Welcome back. In this video, we're continuing with section 5.4 and using systems of equations to help us solve story problems. In this first part, we'll look at some geometry applications. To do that, we need to look at or review the idea of complementary and supplementary angles. So two angles are complementary if they add up to 90 degrees. Examples would be a 50-degree angle and a 40-degree angle. Those would add up to 90 degrees. A 80-degree angle and a 10-degree angle also complementary, add up to 90 degrees. A supplementary angle or pair of angles are supplementary if they add up to 180 degrees. So easy one would be 100 degrees and 80 degrees. Or if you had two 90-degree angles, those would add up to 180 degrees. Complementary add to 90 and supplementary add to 180. Words that go with this are supplement and complement. So here we've described 80 and 10 as complementary. We could also say the complement of 80 is 10, or the complement of 10 is 80. Similarly, 100 and 80 are supplementary angles. We could say that 100's supplement is 80, and also the supplement of 80 is 100. Okay, so that's the terminology we're going to need to help us with these first couple problems. Here, we're told that the difference of two complementary angles is 20 degrees, and we want to find the measures of the angles. So the two angles, the difference, so we're going to subtract them, is 20 degrees. So we'll use X and Y for the angle sizes. The difference is 20. So ordinarily, when we're solving one of these systems of equations, using a system of two equations and two unknowns, we need a second equation. And here, the second sentence is just telling us to find the angle. So where do we get that second equation from? Where we get the second equation from is knowing that those two angles are complementary. If they're complementary, they have to add to 90 degrees. So here we didn't get a whole second sentence telling us that that turns into an equation. It's kind of hidden in the word complementary. Okay, but once you got that, it's kind of downhill from here. Our system is good for elimination. So we'll get 2x is equal to 110, so that x is 55. Once you have x is 55, then y will be 35. Okay, those two differ by 20, and also they add to 90. Okay, so there's our two angles. All right, here's one about supplementary angles. Two angles are supplementary. That's the first sentence, and that's going to turn into one equation. X plus y equals 180. And then it goes on to say the measure of the larger angle is 18 less than twice the measure of the smaller angle. So I need to describe which one's larger and smaller. Saying they're supplementary here, X or Y could be the smaller one. So I'm going to go and say that X will be the larger one, and then Y will be the smaller one. Okay. Just so that we're sure. You could make the decision the other way around, of course, as long as you make a note of it. Okay, so the larger angle, that's X, is 18 less than twice the smaller. So X is 2y minus 18. That will be our second equation. Okay, so we're going to use substitution this time. X, also known as 2y minus 18, plus y will be 180. So this will be 3y equals 198. And so dividing by 3, yep, 66. So y is 66 degrees. Okay, and then we can back substitute to get the value for x. So x is going to be, eraser's not working. There we go. X will be 2 times 66 minus 18. And so that works out to be 132 minus 18. And that's 134 minus 20. or 114. Okay, I think that will do it. So we have 114 degrees and 66 degrees. Okay, just to check, those two should add up to 180. And they do, and twice the smaller one. And less 18 does work out to be the larger one. So it does work out, 114 and 66. Okay, some more examples to come. Okay, this one kind of geometric, again, kind of longer, but don't be put off by the size of this thing. We can do it. Here it says Mario wants to put a rectangular fence around the pool in his backyard. Since one side is adjacent to the house that is next to, he will only need to fence 3 sides. So a little sketch can help. Here's the house, there's going to be the pool. He's going to put a fence around 3 sides. Okay, there are 2 long sides, and the one shorter side is parallel to the house. So that looks a little weird, but I guess that's the way it is. The shorter side of the rectangle is parallel to the house. The longer sides are perpendicular to the house. Okay, he needs 155 feet of fencing to enclose the pool. The length of the there's a lot here, isn't there? The 155 feet of fencing to enclose the pool, that's going to be our first fact. I'm going to let X be the long direction and Y the shorter direction. Okay, so then we'll have we're not fencing along the house, right? So it'll be 2 X's and 1 Y. That'll be the total of 155 feet of fencing. And then it says the length of the long side, that's X, is 10 less than twice the width, which is the other side, right? Okay, so there's our system of 2 equations and 2 unknowns. On this one, definitely the setup is harder than solving it. We're going to go ahead and solve the system now and see what we get. So we'll have 2 times 2y minus 10 plus y is 155. So we're using substitution here. We'll have 4y minus 20 plus y is 155. And then we're going to just continue with this. Okay, once again, Zoom crashed, but I guess we're okay now. All right, so then this makes our y 35 degrees, not degrees anymore, 35 feet. And then for the x, that's 2 times y minus 10, and that will be 50, 60. All right, so it's going to be 35 by 60. Okay, that'll do it. Okay, next we're going to take a look at uniform motion problems, and once again we did these with single variables. We can do these with 2 variables also if we'd like, but still I'm going to end up organizing the information in a table as I've done before, just to see what's going on. Remember that all of the distance, rate, and time problems are governed by the formula distance equals rate times time. And also what's uniform about these is that nobody's speeding up or slowing down. That's it. Okay, so the question, this is about Pedro and Fredo. And the question, skipping to the end, is how long it takes Fredo to catch up to Pedro. So the answer, how long, is going to be a time. And so let's let X be Fredo's time. Okay. All right. So the story is Pedro left Detroit on the interstate going south toward Orlando at a given speed. Then Fredo left Detroit later, and we want to know how long it's going to take him to catch up. So I like to organize the information in a table. We'll see if we get 2 equations out of this. Distance equals rate times time. And then we had Pedro and we had Fredo. Okay, so I guess we could make 2 variables out of this. X will be Fredo's time. And then here it says that Pedro left first, right? Pedro left earlier. So y will be Pedro's time. And since Pedro left first, his time is one more than Fredo's time. Since he left earlier, he was on the road for 1 hour longer. Okay, so that will be one of our equations. Okay, so then Pedro's time, I got those in the wrong place. So Pedro's time was y and Fredo's time was x. Pedro goes 60 miles an hour. Fredo goes 75. And then since distance equals rate times time, we're able to fill out the distance column as a product of rate and time. So one of our equations is given by the fact that Fredo is going to catch up to Pedro. If he catches up, that implies that the distances traveled by the two people are the same. So the 60y has to equal 75x. And so finally, that's our two equations. So let's go ahead and solve those. What I would probably do first, actually, is I noticed that 60 and 75 are both divisible by 15. So I'm actually going to divide both sides of this equation by 15. Not a necessary step, but I like to look for opportunities to make the numbers smaller. So if you do that, you'll have 4y is equal to 5x. And then we know that y is equal to x plus 1. Okay, so going through, what did I just do? That's just an x. We're replacing the y by x plus 1. And so then it looks like x is 4, and y is x plus 1, and so is 5. So it should take 5 hours. All right, so that should do it. To be honest, I find trying to do this using two variables to be a little awkward. I think these are easier to do just using a single variable. So I'm going to go ahead and check on this one and make sure that it worked. So we found out that the x was 4, and so it should be that 4 times 75, which is 300, that should be the same as 5 times 60, which is also 300. Okay, so the distances traveled by the two people are both 300 miles, and we know that Pedro was the one who left earlier, so he is on the road for 1 more hour. All right, I just felt the need to make sure on that one because, like I said, trying to do this using two variables, I think, just makes it more awkward. Okay, so let's try one more of these, and then I think we're all done. Okay, so take a minute and pause the video, try this one yourself, and then restart the video and see how you did. In this one, Jason paddled his canoe 24 miles upstream for 4 hours. It took him 3 hours to paddle back. We're going to find the speed of the canoe in still water and the speed of the current. All right, so as before, I like to use a table to organize the information. I'll see about using a system of equations to represent this if we want. The two parts of the trip here, this time it's not two separate people traveling, it's one person but doing two separate things. He goes upstream, part of the trip, and then downstream. Okay, let me see what we can fill out. 24 miles upstream. So the distance we've got is 24, and we know it took 4 hours. He's paddling back, so they don't mention downstream here, but he goes upstream for 4 hours, and then when he paddles back, the implication there is that he's going downstream, and it's so the distance is the same, but it only took 3 hours. All right, so what is missing here is the rates, and so on this, we have the speed of the canoe in still water and the speed of the current, that is how fast the stream is flowing. Unfortunately, both canoe and current start with C, so I don't want to do that. I'm going to go with C as the canoe speed, that is how fast he is rowing or whatever. And then instead of current, let's make that the speed of the water. I was going to do stream for a second, but my S's look like 5, so I'm not going to risk it. Instead, we'll make W for water. Okay, how fast is the stream flowing? That's the water. And then canoe, that's how fast he is rowing. All right, so then downstream, the speed that he is rowing, that is his canoeing, is being helped by the water flowing around him. So his overall rate is going to be C plus W. On the way upstream, he is rowing against the flow of the water, so the water is holding back his progress. So his rate is C minus W. Okay, so that is often a little tricky for people to think about. So let's make sure before we go on. If you we're more familiar with riding in cars, so let's do that. Let's say that you're on the freeway going 60 miles per hour, sitting in the car going 60 miles an hour. Let's say that there is a fly sitting on your dashboard, just sitting there. How fast is the fly going? Well, if the fly is just sitting in your car, which is annoying, if it's just sitting there on your dashboard and your car is going 60 miles an hour, the fly is going 60 miles an hour. Okay. Now, let's say that the fly takes off and starts flying back towards the rear of your car at 1 mile an hour. Okay. So your car is going forward by 60, but the fly is heading backward by 1. The fly is still moving forward, but not as fast as it was before. It's moving forward by 59 miles per hour now. 60 miles per hour forward, 1 mile per hour back. If instead, let's say the fly now sitting in the back seat starts flying forward at 3 miles per hour, and you're still going 60, if you were going 60 before and the fly is now going towards the front of the car at 3 miles per hour, it's now going 63 miles per hour. So you need to think about the direction, basically. Are you going for or opposite of the direction of the overall vehicle in which you're traveling? For this guy, Jason, canoeing in the water, when he's going downstream, his canoeing is being helped along by the water. When he is going upstream, the water is, he's going oppositely directed of the water, and so the rates are subtracted. Okay, so hopefully that helps. But now we can go ahead and solve our set of two equations. So we'll have that distance equals rate times time. So 24 is C minus W times 4. And also 24 is C plus W times 3. So we can divide both sides by 4. So we'll have 6 is C minus W. For the other one, we'll divide, there was supposed to be an equal sign in here. We'll divide both sides by 3. So that we'll have 8 is C plus W. So our two equations look like C plus W is 8 and C minus W is 6. Now we can add together the two equations. We'll have 2C is equal to 14, so that C is 7. Now we know the speed he is canoeing is 7 miles per hour. And since C plus W is 8, that implies that the W is 1. So the speed of the stream, or current, I guess they put in the problem, is 1 miles per hour. And then the canoeing, how fast he is rowing, is the 7 miles per hour. Okay, all right, that takes us finally to the end of this section. We did some story problems using systems of equations. We saw that also we could do it without systems of equations too, but that's it. Let me know if you have any